In 1980, a brilliant engineer working quietly in a corporate research lab developed a completely revolutionary microscopic switch. Over the following decades, the quiet deployment of this exact architecture saved the global economy $37 trillion. Today, this silent piece of solid-state physics is dismantling the long reign of the mechanical combustion engine. To understand how a microscopic wafer is displacing the world's heaviest industrial infrastructure, we first have to look at the undeniable physical friction that caused the mechanical age to plateau. For over a century, industrialization required the brute force extraction, transport, and combustion of ancient organic matter. The primary method for converting that matter into usable energy relies on physical violence. We ignite fossil fuels to boil water, generating high-pressure steam simply to force heavy magnetic turbines to spin. Early grids demanded monumental physical space. These heavy metal generators required immense structural engineering just to contain the forces they produced. On a consumer scale, the internal combustion engine requires thousands of separate moving parts, perfectly timed to turn controlled explosions into forward motion. This diagram illustrates the Carnot limit, a strict thermodynamic law dictating that systems relying on mechanical friction and temperature differentials will inevitably bleed energy. Because of these constraints, modern internal combustion engines waste 80% of their generated energy as raw, unusable heat. The entire lineage of mechanical power relies on entropy, a system defined by chaos, extreme temperature spikes, and inevitable material breakdown. Mathematical friction loss is eliminating the internal combustion engine faster than any environmental policy. Solid-state physics provides an environment where friction and moving parts do not exist. This animation shows negentropy in action. Instead of burning matter to create a chaotic explosion, energy is introduced to a pristine crystal lattice, causing a highly ordered, deterministic routing of electrons. The practical application of this physics emerged in 1980, when researcher Jayant Baliga invented the Insulated Gate Bipolar Transistor at a General Electric laboratory. Baliga formulated a mathematical figure of merit, proving that immense voltages required by global power grids could be managed with the digital precision of a computing microchip. A single, motionless switch the size of a postage stamp could now govern the heavy electrical loads that previously required massive rotary mechanical converters. The invention of the IGBT allowed human infrastructure to evolve, from physical brute force to negentropic digital control. As the global demand for power scaled up, engineers discovered that standard silicon had a thermal melting point that limited its industrial utility. The solution required fabricating a material that barely exists in nature. Companies like Wolfspeed spent decades commercializing pure silicon carbide. This microscopic comparison demonstrates why. While the carbon bonds found in fossil fuels violently break to release energy, the specific covalent bonds in silicon carbide hold firm, capable of withstanding 10 times the electric field of standard silicon. This hyper-durable crystal lattice is the architecture preventing modern electric vehicle inverters and high-density artificial intelligence data centers from incinerating themselves. Transitioning to silicon carbide provided the final physical upgrade required to permanently bypass high-voltage mechanical combustion infrastructure. High-efficiency power conversion provides the technical foundation for renewable grids. By minimizing loss during transmission and storage, solid-state systems allow energy networks to detach from the geographic necessity of fossil fuel extraction. This graph tracks Swanson's law. Clean energy infrastructure now behaves like software, experiencing a predictable cost decay of roughly 20% every time global manufacturing capacity doubles. Overlaying that plunging manufacturing curve against the volatile geopolitical friction of extracting oil, the economic reality becomes obvious. To study the analytical frameworks behind this kind of macroeconomic transition, you can explore the specialized courses on deep tech engineering over its sponsor name. Modern energy has transitioned into a scalable technology that we manufacture, rather than a finite resource we must mine. We are steadily exiting a century built on fire and moving into an infrastructure governed by the silent routing of the electron. This frictionless delivery system is what enables the massive digital infrastructure required to process global data and train modern algorithms. Yet, as silicon carbide solves the friction of moving electricity, the processors performing the actual calculations are hitting a physical thermal limit of their own. The ceiling on the artificial intelligence revolution resides in raw, physical thermal heat, rather than the limits of human code. Click the video on your screen to see the radical engineering required to keep the next generation of artificial intelligence servers from melting down.